Okay, so now we're going to do the same problem, but this time we're going to use the vector analysis. And remember, with the vector analysis, we have the moment as a Cartesian vector is a position vector cross force vector, okay? So we're going to be setting up that matrix again, and hopefully we should come up with this same magnitude after we get that Cartesian vector. So when I am looking at taking the moment about point O, I'm going to have this 400 Newton vector, and I'm going to have this 260 Newton vector. And when we're using position vectors, remember, we don't have to find the perpendicular distance. So if I take my vector and I follow along, okay, my vector line, I can come to any point on this vector. Well, I happen to know the coordinates of A, and the coordinates of A are 2, -5. So I'm going to go from the origin, the point I'm spinning around, I'm going to have my position vector from O to A. And that is then touching the line that my force vector of 400 newtons is on. Okay? And then I can do the same thing over here. I have this vector of 260 newtons. We see it goes in that direction. The point that I do know is B, and its coordinates are 6, 0. Okay, so this time my position vector, R, O to B, goes from the origin to point B. So remember that position vector, it always goes from point to the force vector. Okay, so let's write our Cartesian vectors. Position from O to A. We use tip minus tail, and I'm going to start with x's, 0, 0. Okay, tip x, 2, minus 0. 2 minus 0, I is that unit direction that tells us in the x direction. Now we're going to go to the y. We have -5 plus -5 minus 0j plus 0k. We don't have anything right now in the third dimension. Because we are looking at the position vector, our units are meters. So we can say 2i minus 5j plus 0k in meters. And we can do a position vector from 0 to b. And again, I'm going to do the same process. I use tip minus tail, tip of position to tail. So 6 minus 0. That's my x components. 6 minus 0i plus 0 minus 0, 0 minus 0j plus 0k, again meters, so I'm left with 6i minus plus 0j plus 0k in meters. And when I go back and look at this, this is telling me that I'm going to walk 6 units positively on my x-axis. Nothing on the y, nothing on the z. And when I come back and look, I am indeed walking 6 units, 6 meters from the origin to get to point B, which is on my vector. Okay? When I look at the one for position A, it's 2, -5, 0. I'm going to watch. I am indeed walking 2 meters along the x-axis, and then I am indeed walking 5 meters down, and that is where I'm getting to point A. So it does make sense. So now we need Cartesian force vectors. So let's look at vector A, Cartesian force vector. And what we want to remember is that it is letting us know the x component, the I component, okay, j, And then we are in 2D, so we have 0K, and we are looking at newtons. My x component, I already figured out up here, 400 cosine 30. That's the x component. I'm going to pop it down here. Okay. Now the y component. The y component is going up, and I already found that was 400 sine 30. Put that in here, plus 400 sine 30. Okay. Force vector of B, same exercise. I've already figured out the x component. I did that when I did my scalar work up here. I have 5/13 times 260. Okay, so that's I is letting me know that unit direction in the x direction. It's just a unit, it's unitless. That is my x component of my force, plus the y component is 12/13 times 260. So I can come back down here, 12/13 times 260, J plus 0K, because we are working in 2D, newtons. So I have my force vectors and I have my position vectors. And now what I can do is set up the matrix for both of them. Okay, so I need to remember that my matrix, my Cartesian vector, equals R cross R cross M, actually R cross F. I don't know where I'm going with this, okay? I, J, K, position, force, always. Okay, I, J, K, position, force. So if we're looking about the moment of point O, it is going to equal I, J, K of vector A plus I, J, K of vector B. I have my position 2, -5, 0, 6, 0, 0. Those are my two position vectors. And now I can look at my force. And I'm going to have 400 cosine 30, 400 sine 30, and 0. And then I'm going to have 5/13 times 260, 12/13 times 260, and 0. Okay. So now we get to do a little multiplication here. When I'm working with a matrix, I'm going to start with the I, and I'm going to cover it up, cover up the I. I'm going to cover up the top, and I am left with a little box here. And I'm going to do a little fish. I'm going to start at the left. I'm going to go down, and then circle back around and go down. Okay, so I have 5, -5 times 0 minus 0 times 400 sine 30. Okay, times I. Minus, I always go minus, it's positive I minus J plus K. Just remember that in your head. I'm going to do the same thing, cover up, and I have 2 times 0 minus, so 2 times 0, fish it back down, minus 0 times 400 cosine 30, J, plus, cover up, 2 times 400 sine 30 minus -5 times 400 cosine 30. So 2 times 400 sine 30 minus -5 times 400 cosine 30. Okay. Okay, so I got my first little matrix done. Plus, we do the same thing for our second. Cover up the I, 0 minus 0, so I have 0I plus, oh, we don't do a plus there, do we? Never, ever, ever, ever. It's always I minus J plus K, minus. Okay, 6 times 0 is 0, minus 0 times that is 0, so minus 0j, cover up by k, plus 6 times 12/13 of 260 minus 0. Okay. And then all of this, we're going to put it is going to be Newton meters because we have our units of meters and newtons, meters and newtons. When we simplify, when we work this out, then this is 0, and we're left here with this value. So we have 2, 400, enter, 30 sine, 2, 400 times 30 sine times, minus a negative makes a positive, 5, 400 times 30 cosine times, plus, so we get 0i plus minus 0j plus 2132 k Newton meters plus 0i minus 0j plus 12 divided by 13, 6 times 260 times, we get 1440 k Newton meters. And when I add this up, 0i plus 0j plus 3,572 k Newton meters. So now we have a Cartesian vector representing that moment. Okay, and we have a 0 and a 0 for my x and y. The moment is wrapping around the z-axis. And we're going to go back and ask ourselves, does this make sense? Well, we got the same value here. If we want to find the magnitude to make sure it matches our scalar, then we can go through 0 squared plus 0 squared plus 3572 squared. And indeed, our moment magnitude is 3,572 Newton meters. Okay, so we end up with the same magnitude. Why is it around the z-axis? If I come back, right-hand rule, I have my x going to the right, I have my y going up the page, and when I stick my thumb on here, this is the z-axis coming up out of the paper. And if I put the butt of my hand on the ordinate here, as soon as I am spinning around, I can see these are actually wrapping around the z-axis. When I have my clock handle and I spin it, it's wrapping around that pin that would be holding the handle in. So this makes sense that I have a z component only for my moment, and I don't have x or y because we truly are wrapping around the z-axis.